Hey everyone, and welcome. If you've ever worked with a huge list of data and needed to ask questions about different sections of it, you've probably felt the pain of how slow that can be. Well, today we're going to pull back the curtain on a total powerhouse of a data structure that solves this exact problem, the segment tree. Let's get right into it. So, here's what we've got on tap. First, we're going to set the scene and understand the problem we're trying to solve. Then, we'll introduce our hero for the day, the segment tree itself, and see how we actually build the thing. After that, we'll unleash its true power with querying and updating, and finally, we'll look at where this awesome structure actually gets used out in the real world. All right, first things first, why do we even need something that sounds so complicated, right? Well, it all kicks off with a really simple and super common problem. Imagine you've got this huge list of numbers, and someone, maybe a teacher, maybe your boss, keeps peppering you with questions. Hey, what's the sum of the numbers from index 2 to 6? Or what's the smallest number between index 4 and 9? I mean, the obvious way to do it is to just loop through that section every single time and add them up. But what happens when that list has a million numbers and you're getting hit with thousands of these questions? That simple little loop? Yeah, it's going to grind to a halt. We need a much smarter way to handle this. And this is where the segment tree comes in to save the day. You can think of it like creating a super detailed cheat sheet for our list of numbers, one that lets us answer those range questions almost instantly. So, what even is it? At its heart, a segment tree is just a binary tree that we build on top of our array. But here's the magic. Every single node in that tree holds a pre-calculated answer for a specific segment or range. The root at the very top, that represents the entire array. As you go down the tree, the ranges get smaller and smaller until you hit the leaves, which just represent one element each. This slide, man, this is where you really see the why. That brute force loop we talked about is O of n, meaning the bigger your list, the slower it gets, 1 to 1. There's another trick called prefix sums, which is crazy fast for queries, O of 1. But there's a huge catch. If you change even one number in your list, the whole thing breaks. The segment tree, though, it hits that absolute sweet spot. Queries are O log n, which is ridiculously fast on big data sets, and it handles updates just as fast. It's the best of both worlds, no question. And it is definitely not a one-trick pony. You can set it up to find the sum of a range, done. The minimum value, the maximum, easy. And it also makes changing a single value, what we call a point update, an absolute breeze. It's incredibly flexible. All right, so we get it. It's awesome. But how do we actually build one? Let's take a look at how we transform a plain old array into this seriously powerful tree. Okay, before we even think about code, here's a super important pro tip. When you're making space for your tree in memory, a really safe rule of thumb is to make it about 4 times the size of your original list. This is going to save you a ton of headaches with weird errors later on. Just remember, 4 times n. The way we build it is actually pretty beautiful. It's all done with recursion. It just follows 3 simple rules. First, if you're at a leaf node, meaning you're only covering a single element, you just grab its value. Easy. If you're not at a leaf, you dive deeper and tell the function to build your left child and your right child. And finally, once your kids are built, you just combine their results to figure out your own value. And this one little line of code, this is pretty much the heart of the whole operation. It's just saying, hey, parent node, your value is whatever you get when you combine your 2 children. In this case, we're adding them. Information just flows up the tree, from the bottom all the way to the top. And you know what the crazy part is? Even with all that recursive work, building this entire structure is a one-time cost that just takes O of n time. You pay this small, efficient price up front to get blazing fast performance for all your questions later. Okay, our tree is built. Now for the fun part. Let's actually use it and see how we get that lightning fast performance we were promised. When we ask our tree a question, it really comes down to 3 simple scenarios. Case 1, no overlap. This is the easiest. If the node's range has nothing to do with the question we're asking, we just ignore it, and this entire branch of the tree, we just walk away. Case 2, this is the one we love to see, full overlap. If the node's range is completely inside the range we're asking about, we've hit the jackpot. We don't have to go any deeper. Boom, you found a pre-made answer. Just take the value and you're done. This is what makes it so fast. And finally, case 3, the workhorse, partial overlap. This happens when the node's range sorta overlaps with our question. We can't take its whole value, but we can't ignore it either. So what do? Simple. You ask its kids. You recursively dive down and ask both children the same question, then combine what they tell you. And here's what's so cool. That whole process for querying, updating a value is almost the exact same dance. For an update, you travel down the tree to find the one leaf you need to change, and then you travel back up that same path, fixing the sums of the parent nodes on your way to the root. And because of this clever design, both asking questions and changing values clock in at that beautiful O log n speed. All right, this is all cool theory, but does anyone actually use this stuff in the real world? You bet they do. Let's look at where this abstract idea becomes a concrete, powerful tool. Ever wonder how a game can instantly show you the players ranked from 10 to 20? That's probably a segment tree at work. They are fundamental to how database indexes can find your data so quickly. Financial systems use them to analyze stock prices over specific date ranges. And, of course, if you're into competitive programming, well, this is your bread and butter. Okay, let's boil this all down. What are the absolute key takeaways? A segment tree is a powerful structure you build on top of an array. Its whole reason for existing is to give you incredibly fast OA log n queries and OA log n updates. It's the perfect tool anytime you have a big pile of data that you need to ask a lot of questions about and maybe change every now and then. And that really brings us to the core idea here. The whole concept of a segment tree, solving a big problem by breaking it down, solving the smaller pieces, and combining the answers, is a massive theme in computer science. And it leaves us with a final thought. What other big, complex problems, maybe even outside of coding, could you solve by breaking them down into smaller, more manageable parts? Thanks so much for hanging out with me today.